Welcome back to Learning as a Hobby, everyone. In this video, I'm going to go over the exercises or some of the exercises, not all of them. There's actually a lot of exercises in this section. But anyway, we're going to go over the exercises for section 1.4 in the differential equations book by George Simmons. Like I said, section 1.4, which I just posted the chapter summary for. It's available now on the channel, so you can watch that if you haven't seen that yet. You should watch that before the exercises, obviously. And I haven't said this in a while, but if you are following along with these videos, first of all, thank you for watching, and I hope you're getting something out of the videos. But as I go through the problems here, you should be trying them on your own before you watch the solutions that I show you here, just so you get the most out of the problems, if that's what you're trying to do. So anyway, let's get to the exercise set. Let me bring up the Jamboard, the Google Jamboards for the problems that I solved. Like I said, I didn't actually do every single problem because there was a lot of problems in this um chapter, or sorry, in this section of chapter 1. I did quite a number of them, though. The ones that I left out are similar to the ones that I did here, so I didn't want to do too many things that were similar to each other. So I kind of picked problems that were of a certain kind, and then did another other problems that were of a different kind, and so on. I say different, they're all kind of related to each other in that the models are all exponential, but well, with some of them are logistic. But anyway, let's go through the problems here. All right, so like I said, this is for section 1.4. I did question number 1, which asks you to do this. So 1 says, if k is a given non-zero constant, show that the function y equals c e to the kx are the only solutions of the differential equation dy dx equals ky. He does give a hint here. He says, assume that f of x is a solution of this equation, and show that f of x over e to the kx is a constant. All right, so that's what I did, basically. I just followed his hint. So here's the proof. Df dx is k f of x. That's the assumption. So we're assuming that f is a solution to the differential equation. Define g of x equal f of x over e to the kx. And then I want to show that when I differentiate that, I get 0 for any x, which means that the function f of x over e to the kx would be constant. So then dg dt equals f prime of x times e to the negative kx minus k f of x e to the negative kx. That's just by the product rule, right? And just using the fact that f prime of x is equal to k f of x, right? That's what we assumed up here. And replacing f prime of x with that, you get k f of x e to the negative kx minus k f of x e to the negative kx, which is obviously equal to 0. Therefore, g of x, which is f of x times e to the negative kx, is constant. Therefore, that's the only solution. All right, so that's question number 1, relatively straightforward. I skipped over question number 2, I guess. Here's question number 3, though. A bright young executive with foresight but no initial capital makes constant investments of $D per year at an annual interest rate of 100K%. Assume that the investments are made continuously and that interest is compounded continuously. And there's a bunch of parts to this. We'll take them one at a time. Part A asks us to find the accumulated amount A at any time t. So let's start with that part. So going down here, I just used sort of like the differential here. The change in P is approximately K times P delta T. That's because we're assuming that it's a the interest is being compounded continuously, right? So this is sort of like giving sort of that the growth is exponential, right? Times D times delta T. So in other words, remember that the executive is investing an amount of D per year, but doing it continuously. So in other words, over a small increment in time, delta T, he's investing some small portion of that annual amount that he's investing. So that proportion would be D times delta T. All right. And then, divide by delta T, you get delta P over delta T is approximately equal to KP plus D. And then take delta T going to 0, which gives you the derivative. And that gives you the differential equation that we have to solve, which is easily solved by separating variables, which I'm doing down here. And I won't spend too much time on that because hopefully you guys know how to do this by this point. And then when you solve for everything, we get that P plus D over K equals C e to the KT, which means that P of T is C e to the KT minus D over K. And then finally, we can figure out what C is by plugging in the initial amount, which is, at time T equals 0, there's 0 money in the account. So P of 0 is 0, which means that C has to be D over K. And that gives us our model. So P of T is D over K times e to the KT minus 1. That's how much money is in the account at time T. So that's the answer for part A. You could also derive this using infinite series, which actually I did that as well. I didn't write that down as a solution here, though, because I wanted to do it using the sort of information that he gave us in the section, which is basically solving a differential equation. So I didn't write down that solution, but you can just, so you're aware, and you might want to try it yourself. You can actually solve this using infinite series as well. But anyway, let me go back up to part B then. So B says, if the interest rate is 6%, what must D be if $1 million is to be available for retirement 40 years later? All right, so going down here to my answer for part B. So I want P of 40 to be 1 million, or in other words, 10 to the 6. And then just plug in your values. So plug in the numbers that they gave us. And that tells us, when you solve for D, that tells us that D has to be $5,986.13. All right, that's the answer for part B. Like I said, just solving an exponential equation, which is, actually, it's not even exponential, it's linear, but you have to plug in the numbers into the model. So part C, if the bright young executive is bright enough to find a safe investment opportunity, paying 10%, what must D be to achieve the same result of $1 million 40 years later? It is worth noting that if this amount of money is simply squirreled away without interest each year for 40 years, the grand total will be less than $80,000. Okay, so that's part C. Going down here, again, we could solve for D in that case just by replacing the 6% with the 10%, which in decimal is 0.1, and just solving for D again, you get this number here, $1,865.74. Okay, so that's the answer of part question 3. Question 4 is very similar, except here, instead of investing, sort of, I guess, like a kind of an annuity situation, this is sort of like a payout annuity situation where you're withdrawing money from an account that's paying you interest. So anyway, let's read through it. A newly retired person invests total life savings of P dollars at an interest rate of 100% per year, compounded continuously. Withdrawals for living expenses are made continuously at a rate of W dollars per year. Right. Part A asks, find the accumulated amount A at any time T. I'll go through this one kind of quick because it's virtually identical to question number 3, but here's the derivation of the solution for part A. So dA dt is Ka minus W. Again, separate your variables to solve the differential equation, and you get the model down here. A of T is P minus W over K e to the KT plus W over K. And now we can use that model to solve whatever problem they want us to solve, which there's several parts here. So part B asks, find the withdrawal rate W0 at which A will remain constant. All right, so going down here, we want so here, if I plug in W0, we want to figure out what W0 has to be in order to make the amount of money that's in the account always be the same amount. So in other words, we're just sort of like using the interest off of the principal that's invested in there or whatever. Right. So here, I'm just rearranging some things and then solving for W1 W0. So when you rearrange stuff here conveniently, on the left hand side you get P times 1 minus e to the kt. On the right hand side you get W0 over K times 1 minus e to the kt. And notice that the 1 minus e to the kt's cancel. You can divide out by them, and then you get W0 has to be P times K, right? So that's the amount that you can withdraw every week or whatever. I forget what the time period they said it was, but that's how much we'll keep the amount constant in the bank account or whatever. All right. It's the withdrawal rate. Sorry, the withdrawal rate. Okay, so C, if W is greater than the value W0 found in part B, then A will decrease and ultimately disappear. How long will this take? Right, so here we want to solve for time. This was part C, right? Okay, so if I want the amount in the account to be 0, I'm just plugging that in for P, and then you solve for T. It's just an exponential equation, so you solve for that, and you get that the time is 1 over K times ln of W over W minus W0. Okay, and then part D, find the time in part C if the interest rate is 5% and W is 2W naught. And again, you just plug those numbers in and solve for T, and you get that it's approximately 13.86 years, or roughly 14 years, right? That's question number 4. Then it looks like I skipped all the way up to question number 8. It is estimated by experts on agriculture that 1/3 of an acre of land is needed to provide food for one person on a continuing basis. It is also estimated that there are 10 billion acres of arable land on Earth, and that therefore the maximum population of a maximum population of 30 billion people can be sustained if no other sources of food are known. The total world population at the beginning of 1970 was 3.6 billion. Assuming that the population continues to increase at a rate of 2% per year, when will the Earth be full? What will the population be in the year 2000? Remember, this book was written in 1950, so I don't know if these numbers are accurate still today, but we'll use the numbers that he gives us. So P is 3.6 times 1.02 raised to the T power. That's from the information they gave us. So in what year was the initial population given? I forget now. The total world population at the beginning. Oh, sorry, this book was written in the 70s, I guess. Total world population at the beginning of 1970 was 3.6 billion. All right, so that's the initial population, and then it grows by 2% per year, so 1.02 raised to the T. Okay, and they want to know when the population will reach its I guess conjectured maximum, which would be 30, I think they said 30 billion or something. So solve for T, and that gives you that the world population will reach its maxima in the year 2077, or in other words, 107 years after 1970. So you just add 107 to 1970. And then the second part was, what did they want to know in the second part? When will the Earth be full, and what will the population be in the year 2000? So you just plug in the year 2000 is 30 years past 1970, so you just plug in 30 there, and you get 6.5 billion people in 2000, which I believe is actually relatively accurate. I didn't look up the numbers, maybe I should have, but I think the world population was around 7 billion in the year 2000. If I'm wrong, you can correct me in the comments. But, all right, question number 10. In example 2, assume that living space for the colony of bacteria is limited and food is supplied at a constant rate, so that competition for food acts in such a way that ultimately the population will stabilize at a constant level x1. X1 can be thought of as the largest population sustainable by this environment. Here, when they say example 2, they mean from the section in the textbook. We went over the exponential growth model for bacteria and like a nutrient solution. Here, the difference is that there's limited resources in space. So you have a sort of like a carrying capacity of the environment, which is X1. Assume further that under these conditions, the population grows at a rate proportional to the product of x and the difference x1 minus x, and find x as a function of t. Sketch the graph of this function. When is the population increasing most rapidly? I just realized I didn't graph the thing, but I'll do it on. I can graph it after we go over the problem. So okay, solution dx dt is kx times x1 minus k, because they said that the rate of change was proportional to x times x1 minus k minus x. So k is the constant, the proportion constant. And then again, this you can solve. Well, actually, solving this is a little bit more complicated. I didn't write all the work for solving this integral because you have to use partial fraction decomposition to first you use separation of variables and then you use partial fraction decomposition to do the integral on the left hand side. So I actually didn't write the work for that, just because I didn't want to waste the space on the Jamboard here. But when you do solve that, you get that x over x1 minus x equals c times e to the x1 kt, and then you do some algebra because you want to solve for the value of x on one side, which I'm doing here. And then when you do that, you end up with this function here. So x is x0 times x1. Remember, x0 is the initial population. x1 is the carrying capacity of the, I don't know, the petri dish or whatever it is that these bacteria are living in, divided by x0 plus x1 minus x0 e to the negative x1 kt. Right. I found this by plugging in, the initial value x0. So in this equation here, if you plug in, sorry, over here, if you plug in 0 in for t, you get that c has to be x0 over x1 minus x0. And then plugging it in and just simplifying everything, you get that thing. All right. So that's the function that gives you the population at time t. And now I forget what they ask us to do again. Find x as a function of t. We did that. Sketch the graph, and when is the population increasing most rapidly? Let me draw the graph first. Just I'll do that on the side here because I forgot. I just realized that I forgot to graph the function. But if you do it, I won't do it exactly, but I'll graph it approximately. Let me do this on the whiteboard so that it's easier to see. All right, so let me draw the axes here. Let's say this is the x-axis, this is the t-axis. Okay, and let's say this is the starting population, and let's say this is the carrying capacity. So this is sort of like a limiting value, right? The graph of the maybe I should do it in red. The graph of the function will look like this, right? If you graph it to the left of when for negative time, it'll extend like this, but we don't care about that because we're starting at time t equals 0. So that's approximately what the graph would look like. Let me go back to the notes now. All right, and then they wanted us to, let me just double check and make sure I shared. Okay, so they want us to find when is the population increasing most rapidly. So to do that, we need to find the maxima of the derivative, which is dx, given by the differential equation here, dx dt equals kx x1 minus x times x1 minus x. You could actually, do this by differentiating the explicit function that we found here. Find the derivative of this, then find the second derivative, and then we're trying to maximize, and the third derivative, we're trying to maximize the derivative function. So we're going to need to find its derivative and its second derivative. But if you look at this function, this is not going to be fun to differentiate. So I don't feel like differentiating this. So what I did was I just used the differential equation. So here, dx dt, we already know the derivative of x is k times x1 minus x. You can differentiate that again using implicit differentiation. Let me just show you what I mean on the whiteboard, just because it makes your life a whole lot easier. So here, that remember dx dt is kx times x1 minus x. If I differentiate both sides here, again, with respect to time, and using the product rule, I get k times dx dt times x1 minus x plus kx times minus dx dt. And then you can simplify this to, let's see, I can factor out a k and a dx dt, and I'm left with x1 minus x minus x, which is k dx dt times x1 minus 2x, and then I can replace dx by this. So d squared x dt squared is k times k squared times x times, whoops, I don't need this parentheses here. K squared times x times x1 minus x times x1 minus 2x. So that gives you the second derivative, and you can differentiate that again using the same process to get the third derivative. So that's where I'm getting my derivatives on the Jamboard here. I just didn't want to write all that stuff out on here. So that's how you get the second derivative, and using a similar process, you get the third derivative, which I have written down here. All right, so the first derivative is what we want to maximize, because they said when is the, if you go back up to the question here, when is the population increasing most rapidly? So take the, when the second derivative is 0, those give you your critical numbers for the first derivative. So that happens when x is 0, x equals 1/2 x1, or x equals 1/2 x1. But the first and the last values are not possible for any value of t. So the only possibility is the middle one, and we just have to show that it gives a maximum by using the second derivative test, but we're doing it for the first derivative, so actually it involves the third derivative. If we solve for when the third derivative is 0, that happens when x is 0 and when x is x1. Remember, those weren't possibilities for critical numbers up here. And if you notice, the third derivative is negative for all x values between 0 and 1/2 plus √3 over 3x1. That's what I'm doing over here. And notice that 1/2 x1 is less than 1/2 plus radical 3 over 3x1. And that means that gives a maximizing value by the second derivative test, right? But again, remembering here, I'm looking at the third derivative because that's the second derivative of the first derivative. So this value of the population gives a maximizing value. That's when the population is increasing most rapidly, right? It's halfway between x0 and x1, or halfway between the 0 and the carrying capacity. All right, next one, question 11. Nuclear fission produces neutrons in an atomic pile at a rate proportional to the number of neutrons present at any moment. If N0 neutrons are present initially, and N1 and N2 neutrons are present at times T1 and T2, show that this formula holds. N1 over N0 to the T2 equals N2 over N0 to the T1. I don't know anything about these nuclear processes, so I don't know if this formula is particularly important in nuclear physics. I'm sure that it is, otherwise he wouldn't be giving it as an example, but I've never seen this before. But anyway, we don't really have to know anything about nuclear physics in order to solve this problem. It's just a differential equation. So N of t is given by N0 times e to the kt. All right, so n of t1 they told us was n1. That gives me that e to the k t1 is n1 over n0. Same thing for n2, n of t2. You get n2, which is equal to n0 e to the k t2. Or in other words, e to the k t2 is n2 over n0. And then, for both of these equations here, where's my pen? We can do this in red just so it's easy to see. I can raise both sides here by 1 over t1 power, 1 over t1 power. Here I can raise this to 1 over t2 power, 1 over t2. Okay, here they cancel. And that gives me that e to the k is equal to this part, and e to the k is also equal to this part. So setting those two things equal, you get this expression here. And then just take both sides to power of t1 times t2, and you get the formula that they wanted us to derive. Right, so that's question number 11. All right, question 16. Suppose the two chemical substances in solution react together to form a compound. If the reaction occurs by means of the collision and interaction of the molecules of the substances, then we expect the rate of formation of the compound to be proportional to the number of collisions per unit time, which in turn is jointly proportional to the amounts of substances that are untransformed. A chemical reaction that proceeds in this manner is called a second order reaction, and this law of reaction is often referred to as the law of mass action. Consider a second order reaction in which x grams of the compound contain ax grams of the first substance and bx grams of the second, where a plus b is 1. If there are a times capital A grams of the first substance present initially, and b times capital B grams of the second, and if x equals 0 when t equals 0, find x as a function of the time t. And here he says if you want to learn more about, first and second order reactions in chemistry, see chapter 16 of General Chemistry, 3rd edition by Linus Pauling, which I just want to make an aside about because I do have this book. Let me stop the screen share for a second. So I do actually have Linus Pauling's book on general chemistry, which I might use as a supplementary textbook when I actually get around to Gen Chem on the channel. So I just wanted to show that Linus Pauling was a very famous chemist. And I guess this book is a sort of like a classic in literature. So anyway, good. That's sort of an aside. Let me go back to the problems here. All right, so just using the information that they gave us, ax0 has to be little a times capital A, and so on and so on. We get our differential equation here, dx dt equals k times little a times capital A minus little ax times b, little b times capital B minus little bx. And again, you could solve this by first separating variables, and then you have to use partial fraction decomposition on the left-hand side so you can integrate. And when you do that, you get this expression here, and you can solve for x, which I do. Where's my pen again? Okay. When you solve for x, you get this expression here. Whoops, this one here. And then you can solve for the constant c, and when you do that, you get the actual formula for the second order reaction. All right, let's see. That's question number, I already forgot what number it was. 16. All right, going on. Like I said, I did do a lot of these problems. And believe it or not, there were more. There was a ton of problems in this section. So, but anyway, there's a few more problems to go through. So question number 20 I did next. An aquarium contains 10 gallons of polluted water. Filter is attached to the aquarium, which drains off the polluted water at a rate of 5 gallons per hour and replaces it at the same rate by pure water. How long? Oh, it looks like the Jamboard copied that weirdly. Let me read it out in the book. Question number 20 says, an aquarium contains 10 gallons of polluted water. A filter is attached to this aquarium, which drains off the polluted water at a rate of 5 gallons per hour and replaces it at the same rate by pure water, how long does it take to reduce the pollution to half its initial level? Right, so that's what we want to solve. I hope the rest of the Jamboard doesn't have an issue like that, but I guess we'll see. Okay, so here x of t, I guess I'm calling grams of pollution present in the aquarium at time t. Dx dt is the difference between the amount of grams of pollution coming in versus minus the amount of pollution in grams going out. So in other words, there's 0 grams of pollution coming in because it's only pure water that's being input into the system, right? And you have so the input is 0 grams of that pollution, and the outgoing pollution is x of t over 10 times the 5 gallons per hour, or whatever it was that they said coming out. It's negative because it's exiting the aquarium rather than coming in. So you get 0 minus this, which is 0 minus 5/10 x, which is just a negative 1/2 x. Right, and then solving that differential equation is straightforward. Again, just separate variables, etc. You get this equation for the system, and c is x0, so you just plug it in, whatever the initial amount of pollution was, and then we can solve the problem that they're asking us to answer. Right, they want to know how long it takes for half of the pollution to exit the system or exit the aquarium. And you just do, solve this exponential equation to do that. So you get t equals 2 ln ln of 2 hours, whatever that is. I didn't actually write down the approximation, but whatever that number comes out to. All right, question number 22. According to Lambert's law of absorption, the percentage of incident light absorbed by a thin layer of translucent material is proportional to the thickness of the layer. If sunlight falling vertically on ocean water is reduced to 1/2 its initial intensity at a depth of 10 feet, at what depth is it reduced to 1/16 its initial intensity? And they want us to solve this problem by merely thinking about it, and also by setting up and solving a suitable differential equation. Thinking about it should be clear. It's very similar to sort of like the radioactive decay problem, right? So you think 10 feet is sort of like the half-life. It's a measurement of distance, not time here, but every 10 feet the intensity of the light is reduced by half. So that means if you want 1/16 the intensity, so you go 10 feet down, it's half as intense. You go another 10 feet down, it's 1/4 as intense. You go another 10 feet down, it's 1/8 as intense, and another 10 feet, which is 40 feet in total, you should get 1/16 the original intensity. And then we could also solve, so that's just intuitively by just reasoning through what the information is with the information that they gave us. But we can also solve it using differential equations. So here I called I just to represent the intensity of the light. So di dx is negative ki. Solve that differential equation, we get this exponential model here, and we can use that I guess quote unquote half-life. It's not a time, it's a half distance. I don't know what to call it, but plugging that in, you get k has to be equal to ln2 over 10, which gives us I equals I0 times 2 to the negative x over 10 when you substitute in the value of k, just to in case it's not clear. I of t is c e to the negative kt, so negative ln2 over 10 t, but you can simplify the e to the negative ln2, or actually you can write this as e to the ln2 times negative t over 10, and this simplifies to give you 2, so you get c times 2 negative t over 10. C is the initial intensity, so I just replaced it with I0, right? And then you just plug in 1/16 in for I, and sorry, actually should be, I0, but you can divide out by I0. So 1/16 equals 2 to the negative x over 10. That's a simple exponential equation to solve, so x has to be 40 feet, right? 25. Assume that the rate at which a hot body cools is proportional to the difference in temperature between it and its surroundings, which is called Newton's law of cooling. A body is heated to 110 degrees Celsius and placed in air at 10 degrees Celsius. After 1 hour, its temperature is 60 degrees Celsius. How much additional time is required for it to cool down to 30 degrees Celsius? Right, so we're using Newton's law of cooling for this, so which says that the change in temperature is proportional to the temperature at time t minus the I don't know what we call it, the ambient temperature, I guess, the temperature that's outside the object. So dt over dt is k times t minus t0, where t0 is the outside temperature, or the ambient temperature. We could solve this easily, again, using, separating variables, etc. And we get our model, which is down here. All right, when you simplify the value of k and everything. And then they wanted us to say how much more time, how much additional time is required for it to cool to 30 degrees Celsius. So you just plug in 30 degrees in for the value of t and solve for the time up here, which again is a simple exponential equation. And when you solve it, you get 2.3 hours in total. But remember, they said that after 1 hour, it had, what was a body is heated to 110. After 1 hour, its temperature is 60 degrees. So just subtract off that 1 hour, and you get 1.3 hours after, the temperature was 60 degrees. It takes an additional 1.3 hours to cool down to 30 degrees, right? Like I said, this is a type of problem you might even have seen in pre-calculus or Calc 1 or something. Number 28 also involves Newton's law of cooling, but it's a little bit more interesting just because the scenario is I guess that's kind of like a mystery, I guess, or something. But anyway, let me read it. For obvious reasons, the dissecting room of a certain coroner is kept very cool at a constant temperature of 5 degrees Celsius, which is the same thing as 41 degrees Fahrenheit. While doing an autopsy early one morning on a murder victim, a coroner himself is killed and the victim's body is stolen. At 10 a.m., the coroner's assistant discovers his chief's body and finds its temperature to be 23 degrees Celsius. And at noon, the body's temperature is down to 18.5 degrees Celsius. Assuming the coroner had a normal temperature of 37 degrees Celsius, which in Fahrenheit is equivalent to 98.6 degrees, when he was alive, then figure out when he was murdered. So you can use Newton's law of cooling for this. T0 is 5 degrees. That's the temperature of the coroner's office or whatever. And T0, the coroner's initial temperature before he was murdered, was 37 degrees Celsius. So T of T1 is 23 degrees Celsius. Right at noon, they said, I think it was noon, they said his temperature was 23 degrees, right? Let me just double check. Sorry, 10 at 10 a.m. At 10 a.m. his temperature was 23, and then at noon it was 18.5. So at noon, or in other words, at T1, the temperature was 23. At T2, which was noon, I'm sorry, T1 was 10 o'clock. T2 is noon. His temperature was 18.5. Noon is 2 hours past 10, so T2 is the same thing as T1 plus 2. So plugging everything into the exponential model you get using Newton's law of cooling, we get that e to the negative k T1 is 18 over 32. And then also we can use the fact that T2 is T1 plus 2. So you get 18.5 equals 5 plus 32 e to the negative k times T2, which is the same thing as 5 plus 32 e to the negative k T1 plus 2. And then we could substitute in e to the k negative k T1 over here. And we can solve for k by doing that. So remember, e to the negative KT1 is 18 over 32. So we get this is equal to this. We can solve for K, which gives us our temperature model here. And then we can use that to figure out when the coroner was murdered. So 23 equals 5 plus 32 times 13, just using the model that I have here. I'm plugging in 23 in for that to figure out how many hours that it took for that to happen. It looks like it took 4 hours for that to happen. So 10 a.m. minus 4 hours gives you the time that the coroner was murdered, meaning that it was 6 a.m. when he died. Right. 29. I think this might, this is the last problem in the section. I realize this is a lot, but anyway, 29 deals with the radiocarbon dating stuff that he was talking about. The radiocarbon in living wood decays at the rate of 15.3 disintegrations per minute, or DPM, per gram of contained carbon. Using 5,600 years as the half-life of radiocarbon, estimate the age of each of the following specimens discovered by archaeologists and tested for radioactivity in 1950. Question part A says a piece of chair leg from the tomb of King Tutankhamun, which was, I guess, in the year 1950, was found to have decay per minute of 10.14. And then they give us a bunch of other ones here. Let's do them one at a time. For part A, so first off, using the half-life, we get our decay model over here. All right, we've done that a bunch of times already today, so I won't go through that process. But anyway, then we can set the 10.14 decay disintegrations per minute equal to the model, and solving for T, we get that the chair leg in Tutankhamun's tomb was 3,323 years approximately before 1950. That's how old it is, at least at that time. And we could do the similar thing for the other problems that they asked us for here. Whoops. Part B, they give us a piece of a beam of a house built in Babylon during the reign of King Hammurabi. In 1950 was found to have 9.52 disintegrations per minute. And if we go down to part B, just plugging everything in, it looks like that tree was cut down 3,830 years before 1950, the year 1950. Part C, dung of a giant sloth found 6 feet 4 inches under the surface of the ground inside Gypsum Cave in Nevada, and that was found to have 4.17 disintegrations per minute. Plugging that in, we find that that happened around 10,502 years before 1950. And lastly, a hard atlatl, which is a type of spear thrower found in Leonard Rock Shelter in Nevada, was found to have 6.42 disintegrations per minute. And again, plugging into the formula, we find that was constructed, or the tree that was used to make it was cut down in 7,016 years before 1950. So that's how old the atlatl is. All right, and that's the last problem that I did in this section. Like I said, there was a bunch more, but they're all kind of similar to the other ones that I already did. But yeah, this was an interesting chapter. I enjoyed going through these problems anyway, even though they're relatively straightforward. But the next section in the Simmons book deals with sort of like ballistic motion and stuff like that. So we'll be doing similar things to that section in the Taylor book in chapter 2. But we'll get through that one next. And then I think there's a section, the last section in chapter 1 deals with the brachistochrone problem. And then there's a sort of like an appendix on differential equations and probability theory, but there's no exercises for that. So I guess I'll just go over the summary of what he says in that appendix. And then finally, we'll be up to chapter 2, which deals with first order linear differential equations. All right, so the next video I'm going to do, though, is the summary for section 1C in Axler. So keep an eye out for that. And I'm going to also do, like I said in the last video, sort of like a just a vlog on where the channel's at and everything. So I'll see you guys in one of those videos. Until that time, keep learning. And if you could do me a favor and like and subscribe if you do enjoy this content. does help the channel grow, and it helps to YouTube to know to recommend the videos to other like-minded people, so that the community can grow, and you know, we can all enjoy the beauty of mathematics and physics and science and so on. So I'll see you guys in the next one. Have a great day.